Good morning. We must start this morning session, and the first talk will be presented by Professor Brosseau, University of Brest, France, with the title Electromagnetic and Ferroelectric Response of Graphene Polymer Nanocomposites. Please.
Okay, thank you very much, Mr. Chairman, and it's a great pleasure to be here, and I would like first to thank very warmly the organizers of this wonderful conference for giving me the opportunity to talk about this subject and to give you just a flavor of what we're doing in our lab. We're trying to manipulate electromagnetic wave, not for a theoretical standpoint, but we're trying to make electronic devices like waveguides, actuators, sensors. And one of the basic difficulty, at the very basis of the system, is to find relevant materials. And we know that homogeneous materials, in fact, cannot possess multifunctional characteristics. It means that basically, if you want to have a material which have magnetic, dielectric, thermal, mechanical properties, you cannot find the good material. So basically, we rely on composite materials, which are very well suited to realize this multi-functionality. And one of the basic issues we have to deal with is to optimize microstructures or nanostructures for engineering what I call cross or product properties. Well, one very important cross property is the piezoelectricity. So piezoelectricity is the generation of an electric field when you put some pressure. Can constraint on the system, or it can work the other way. So when you put an electric field in the materials, you can generate a variation of the volume. So another interesting product we're working on is the product effect, like typically the magnetoelectricity. So magnetoelectricity, you have two ways to realize this. So it's the direct coupling between the two order parameters of the system, polarization on the one hand, and magnetization on the other. So you can directly realize the coupling, but the experience tells us that it's very difficult to realize in practice, and the magnetoelectric effect is very weak, and it requires very low temperature. The most effective way to realize the coupling between the two order parameters is to use mechanical constraints. So it is called extrinsic magnetoelectricity. And the experimental realization is represented by this results, which has been done using thin film geometry. So basically, you can use a nickel iron oxide, NFO, on top of the barium titanate BT, and over a certain was based on transfer, but it's not important. So basically, when you excite the system, so the two thin film series, by this magnetic signal, so you don't observe any voltage variations at each phase, so either in iron oxide or iron titanate. But when the two thin films are in series, so you can clearly measure signals, so which is the proof of principle that you have realized cross-coupling between the polarization of the barium titanate and the magnetostriction of the iron oxide. So this was a result which is pretty whole, and this was the first proof of principle of this effect. So basically what we realized is very similar, but we don't work with thin film. We work with nanocompacts. So basically we use nanopowders of nickel, which is a transition metal, very conductive, magnetostrictive, and barium titanate, which is ferroelectric, piezoelectric. And when you compact both powders, you put some pressure, like a protocol. So you can raise this compact like this, and you can cut the compact and make the characterization you want. So basically what we were about to do is to measure the variation of the permittivity, either the real part or the imaginary part, epsilon prime or epsilon double prime, versus the magnetic excitation. And when you look at the cross-coupling, it's very important to realize that this effective parameter is very well correlated to an internal a local parameter, which is the internal field measured by FMR for a magnetic resonance. So this is a good indication that what you measured has some microscopic coupling origin. And what is also important to notice in this data is that the peak here in the coupling is very well correlated to the percolation threshold of the system, because remember that nickel is very conductive compared to barium titanate. And this result is exactly what some people measured a few years ago, because they used thin film geometry again, PZT with tafenol, which is a piezoelectric, and the cross coupling, the microelectric coupling, has exactly the same shape with the peak, and which is also correlated to percolation threshold. So this is low frequency behavior. This is microwave behavior. Okay, so this was the first proof of principle that the microelectric effect can be very effective, can be viewed at this very high frequency. So is that useful? Because we're basically we're interested in innovative material for microwave devices. So a few years ago, I was aware of this very interesting, very clear paper, and what this guy realized, in fact, that using still thin film geometry with a piezoelectric phase and a magnetic phase, they put this on the transmission line, they feed it with some power, and they measure the reflected power. And what they observed is that there is a peak central here, and they can blue shift or red shift this peak by applying a voltage gradient right here. So what we did is, using a material, nickel and barium titanate, we exactly duplicate the system, but not with electric field excitation, but with magnetic field excitation. And we exactly observed the shift depending on the magnetic field excitation. So this was a very exciting result, and which now is useful for determining what we call phase isolator for microwave devices. Okay, so I won't speak about this today, but I want to speak about nanocomposites with graphene. Graphene has attracted a lot of attention in the recent decades because it's very conductive, and most interesting, it has very large surface areas. So you can have interface effects which are much more important than, for example, carbon nanotubes or carbon black, for example, particle if you work with this. It has a very low density, pretty cheap, and it can be fabricated originally in the lab. So plastic, on the other end, we are putting some graphene particle inside plastics, because plastics has many advantages. You can have any shape you want, and it's very cheap. And there is a tendency actually in the industry, in the electronic engineering, to work with plastic electronics. For example, we can use microelectronic circuits for satellites. It is very relevant for this purpose. Okay, so basically the outline of my talk today is relying on a set of questions. So I want to show you some results about the microwave dependence of the permittivity depending on the graphene content, on the stress you put on the material, on the ferroelectricity of this material, because the PVDF, which is the polymer matrix, is a ferroelectric, very good ferroelectric. Well, it's not entirely PVDF because there's a copolymer, which is a trifluorine ethylene. And the question we want to ask is what is the coupling between conductive fillers and the ferroelectricity of the polymer matrix, because we know that conduction of particle is often detrimental to the ferroelectricity. And the last question is, which is a very basic question for many decades, do we have a theoretical framework to understand the content, or the graphene content dependence of the electromagnetic response? And for that, we have many interesting theoretical framework like Brugman theory, Minfield theory, or two-exponent phenomenological percolation model. Okay, so basically the materials are, so graphene, if you put a cryofracture surface or this sample in TEM, so you got this, you got flakes with typically 1 nanometers thickness and a few microns of size, and the X-ray diffraction show that you don't have any contaminant in the system, and you find the PVDF peaks and also the graphene, which is related at 26 degrees. So basically, to measure the electromagnetic response, we use what is called the transmission light system. So we basically put the system in this. So we create an electromagnetic discontinuity in this line. And what we measured is a reflection or transmission coefficient called the scattering parameters, which are represented by this matrix. And if you do correctly the mathematics, so you have to inverse a problem, and you got simultaneously the permittivity, which is a complex number, and the magnetic permeability also if you have some magnetic species inside your sample. So basically here are the results. So I won't get into the details, so don't worry about that. So as you can see here, you put more and more graphene in the system, and intuitively you can imagine that it will render the system more conductive, so the permittivity is higher. And what is equally important to notice is the dielectric losses are very low in the system because you don't have any free current in the system. Okay, so another remark, which is also important, is when you change the VDF ratio, I mean the copolymer ratio in your system, so you can have different behavior because this ratio directly impacts the crystallinity of the system. And remember that the graphene particles are embedded only in the amorphous phase of the system. So a few years ago, we devised a very unique system which is able to measure the electromagnetic parameters, so using a network analyzer, when the sample is submitted to an elongation ratio. So basically, this is an analyzer network right here, and this is the test cell. So this is input power, transmitted power, and you exert a force in this direction. Okay, so you just turn the wheel, and you can have an elongation ratio which can be pretty high depending on the elastic property of the material, because you can have up to 1 order of magnitude in the length of the system. So before entering into the data, I think it's important just to pause a moment and to see what happens from this theoretical standpoint. So basically in our system, which is semi-crystalline, you have crystallites here, random amorphous chains, and the black dots represent the aggregates or the agglomerates or particle, if you want to simplify the system. So basically what happens when you exert a force is that the average distance between if you pick 2 aggregates or particles is increasing depending on the magnitude of the force. And when you put in this equation, which is the free energy of the system, you can have access to the constraints, and you got exactly an equation of state which looks like this. So this is important, the important term of what is called the Gaussian molecular network model, which depends on lambda, which is the elongation ratio, minus 1 over the square of lambda. And basically it states that when this law is experimentally checked, so you get a system which is pretty similar to an elastomer with volume invariant in the deformation. So what the experimental tells us is, forget this point, but I will just focus on the decreasing part. So this is a decrease, but in fact this is an increase. So this is an increase of permittivity, but since we plot the variation with a minus here, it looks like a decrease. So don't worry about that. So we observe an increase, which looks like this, and which is proportional to the GM&M functional law. So basically in our system, with graphene, with different content of VDF, we have this fit, which looks like linear dependence, and the slope of this linear dependence depend on the VDF contents, on the ratio of the copolymer you have in your sample. So very interesting results, which means that you can control simultaneously the dielectric and the mechanical properties of this sample, which is a very interesting result for actuation application. Okay? So, well, this is a set of conclusions, so I will be very brief on this. So the second issue I want to share the result with you is how the polarization cycle are modified by including graphene into the ferroelectric matrix. So basically, that, as I told you previously, when you put some conductive filler, for example, metal in your system, so generally the ferroelectricity disappears. So what happens? Before looking at this, I will just make a few comments about the measurement method. Basically, we use a capacitive method to measure the minor loops of the system, but we also use another method which is called the Poon method, because when you put some conductive particles in the system, you have to be very, very careful about your conclusion you have and your results, because it affects the minor loop system. So the Poon method is relying on the use of positive and negative voltage pulses, and if you have the same result with the two methods, so your conclusion can be very carefully understood. So basically, I show you here some result, which is the dependence of the permittivity versus the graphene function. So it's an increasing function, which can be well fitted using different law. But the most interesting part is this. So you look at the cycle, the polarization cycle, which is very distorted, depending on the VDF ratio, depending on the graphene content. And when you did the Poon method, so you got exactly the same values of the maximum polarization, the coercivity. So even if these loops are not major, because we don't apply sufficient amplitude of the electric field excitations, you can have solid, rock solid, I would say, conclusion, because the two methods give the same result. So basically, we're interested in looking at the two peaks, which in the jargon of ferroelectricity represents the butterfly shape of the cycle, and they represent the two states of equilibrium in a system. So you can switch for your application between one peak to the other, depending on the electric field excitations. And one way you apply this Johnson model, depending on two parameters, A and B, depending on the harmonicity of your model, so you can have a very good fit. So this measurement nicely agree with the theoretical curve, and it can be interpreted with the standard Johnson model, which each of you use is kind of sample. So the third topic deal with the graphene content, and we will focus on this three questions. So do we have a theoretical framework to understand the graphene content of the electromagnetic response, and how the graphene may influence, for example, the microwave absorption, which could be very useful for microwave devices. So here's a set of results which have been done at Coastal Labs a few years ago. So you have the upturn prime and upturn double prime dependence, depending on the frequency of your excitations. And this is typical of non-Debye behavior, which can interpret it using the interfacial polarization modeling due to Maxwell-Wagner Sillars. And when you put some quantitative models, you can find very, very significant result to interpret this kind of materials. And it underlies the role of the interfaces in the system. So when you look at the temperature, you got an Arrhenius don't worry about this complicated behavior. I won't comment on this, but what is much more important is to look at the graphene, the dependence of the permittivity versus graphene, and it can be very well fitted with the TPE model, otherwise stated as a Maclaurin equation, with a set of parameters, and this is a propagation threshold and two exponent S and T. So these are results at a low frequency, okay? And when you do the same measurement, at microwave frequency, you get the spectra, which are pretty complicated to understand. But when you look at the graphene content, you can fit with the same TPP equation, Maclaurin equation, with exactly the same parameters, percolation threshold, and S and T parameters. So S and T parameters, percolation threshold, exactly the same with some uncertainty value, of course. So here is a caveat, in fact, because TPP is not a mean field theory, which relies on first principle of physics. So you have to be very careful when you look at this very good fit, because the interpretation of the percolation threshold is pretty clear. But these two parameters, S and T, differ very significantly from what we call the universal exponent of the standard percolation theory. So you should be very careful to understand such result. Okay, if you look now at the inference of an elongation, so when you exert some force on a system, so you get exactly the same GM&M functional, so the decreasing and the line of fit, which is good. And I told you that previously that this is an indication that the volume is invariant. And you can see this invariance of volume right here, because the distance in the principal direction varies linearly as lambda, and the two other directions, they decreased as a function of 1 over the square root of lambda. So if you multiply 1 of the square root of lambda by 1 of the square root of lambda multiplied by lambda, you get 1. Okay, so the volume is constant. So this is proof, a principle. This is a check that the elasticity network is a relevant model to interpret this kind of result. Okay, so basically, if you look at some applications such as microwave absorption, this kind of sample is not very good, in fact, because I show you a result of the absorption as a function of frequency. So this is kind of experiment we do. So here's a sample. So we can exert some force in some direction with different elongation ratios, and you input some power, you measure the reflected power, and you can calculate what has been absorbed in the bulk of the material. But this kind of result is very poor, in fact. So I would conclude that if you want to use PVDF-TIFE with graphene, it's not very good. You can have much more important and significant results using carbon black particles, using ferrite, metallic and magnetic particles, but graphene is not good. So this is an interesting result, but not for microwave absorption. So is it time for conclusion? So what I would retain from this kind of study is that the graphene field for electric polymer can be useful to simultaneously control the dielectric, the ferroelectric, and mechanical response, probably also the thermal response, but it's not a good sample for microwave applications. Okay, so what's next? Basically, we want to work on this kind of system. So electronic plastics, wearable electronics, and define some material for new types of muscle, artificial muscle for robotics, for example. So we're interested in this kind of application, and we're still working on graphene PVDF because, as I mentioned, you can play with different physical properties. And the main problem in the system, as Luis told you yesterday, is the physical aging of the system. Because if you want to place such devices in, for example, a satellite, so you have this satellite has to work for many years, so it should be very performant in terms of applications. So another more theoretical issue we are dealing with is to understand the role of the interfaces, because the interfaces are very complicated in the systems, and we're trying to model using very simple ideas by describing the interface as a specific phase, which are intermediate properties between the inclusion and the matrix, and using finite element simulations, we can have access to a lot of results and we expect to have a theoretical understanding of what's going on at the interface between the polymer matrix and the graphene content in a few weeks or a few months. So I will finish by some acknowledgement, because it's an international cooperation with Portugal, the next winner of the Football Cup, as I fully understand yesterday. Sorry for Morocco. And a good friend of mine coming from Ivory Coast, which was a former PhD student of mine, and one of my collaborators in Brest. So thank you for your time.
So thank you. Thank you very much for this nice talk. So now we have time for a few questions. So I put a question. So to calculate the permittivity and permeability complex quantities, you need to measure the 4 S parameters. Two.
Yeah.
Only 2. The S parameter, you need a network analyzer.
Yeah.
You use S12, S11, for example. And with these 2 parameters, you can calculate both.
Yes, it is an optimization problem, in fact. You can work with 4. But if you work with 4 quantities, it's much more difficult, because you have to simultaneously solve a direct problem and an inverse problem. So you have to minimize some functional. And if you work with 2 parameters, it's much more simple. But these 2 parameters are complex, of course. So it's 4 parameters, including the magnitude and the phase.
Okay.
But we have an algorithm for that.
And I think it is in slide 11. You showed the system that permits to measure these parameters. Yes. So this is a cavity. This is a cavity inside. Yes.
No, this is not a cavity. This is a waveguide.
Okay.
Okay. It's an open waveguide. It's open air. So the sample is just put on the system.
And you can apply the force perpendicular to this one.
Exactly.
Okay. And you change the frequency. You can change the frequency.
Yes. This is the input, and the input comes from the analyzer.
Yes.
And you can vary the frequency. I think between 0.1 megahertz and 10 gigahertz.
Okay. Thank you. More questions?
Thank you. The model you employ to understand probably the elasticity, I think it's called a affine deformation model. But it seems to me that you assumed that the polymer matrix is fully amorphous, and these are the fillers, if you want, which act as a physical cross links. But you showed us also on your XRD curve that this is a semi-crystalline polymer.
Yes, that's right.
So in fact, you have a smaller crystals which also act as a physical cross links.
It still works because the crystallinity phase is pretty small, in fact.
How much is it?
I would say it's less than 20%. And you can play with that with the VDF copolymer phase. So.
And I assume you have a limit
sure.
on your lambda. If you go to higher lambdas, then you start to invoke.
There are many more sophisticated models to include these crystalline phases, like the Monet-Revlin, for example, model, which is used for semi-crystalline elastomers. Yes, sure.
Okay, thank you.
Hello. I would like to know about particularity of the Gaussian molecular network model. This is a free programs, or is it free? Is it free?
What do you mean by free?
So we can buy it, or we can just found it open source, you mean?
Now, this is a theoretical framework. I mean, you can find it in, for example, the De Gennes book. You know the famous De Gennes book?
Oh, yes.
Yes. This is scaling concept in polymer physics. So it is very well explained. So,
okay.
So it's, But if you want to do simulations,
Yes, this is
I
what
understand your question. Okay.
Yes, exactly.
So there is in COMSOL multiphysics, for example, using finite element simulations, there is a mechanical component which is devoted to polymers, and you can play with that. You can modelize your system. You can put the crystalline phase, the amorphous phase. There is a data bank, a databases, about the different polymers, PVDF, PE, PP, and so on. So the basic data about these materials, including elasticity, modulus, thermal properties, are inside the system. So you can play with that, and you can have a microscopic behavior depending on what kind of mechanical torture you do to your sample. So you can have uniaxial tension, you can have torsion.
Yes.
You can do what you want.
Perfect. Okay, thank you.
No more questions? So to finish, and you show a correlation between the percolation in nickel barium titanate system, this percolation and the parameter calculated. I think it's number 4, slide number 4, and this one, yeah. What is the critical percolation concentration that you calculate here?
It's right here when the connectivity lift on.
Yes.
You can put it. You can choose it at the right of the middle, but usually this is not a good way to determine the percolation traction because, in fact, you have to use another representation depending of the connectivity plotted versus the shift versus the pseudo percolation traction, and there is some divergence, and from the linear part of this divergence you can have the slope which define the critical exponent and the percolation traction.
Yeah, but I was trying to do that and to see perhaps 20% in this case.
Yeah.
And why is so high this percolation? 20%.
I would say that when you have this kind of systems, in fact, you don't play with nanoparticles. You play with clusters or nanoparticles. So when you look at the standard percolation theory for spherical particles, so the theoretical calculations tell us that the percolation threshold is about 17%. So we're pretty close from there, and it depends also on the way you fabricate the materials. Well, there are many parameters. So percolation theory is in fact very easy to do when you do theory, but when you get complicated. So.
Okay, thank you very much indeed.